So we've said many times that proteins are simply linear polymers made from amino acids strung together by peptide bonds. And as we prepare to start talking about real protein structure, there's one more thing I want to do to bridge from our previous chapters on amino acids and peptides to proteins. And that has to do with some terminology regarding the size of proteins. Here down at the bottom is a protein that we call the green fluorescence protein. And as I've said many times, this looks like a piece of fettuccine that's all curved up on itself. This is actually a linear chain. It starts at one end at the amino terminus and ends at the other end at the carboxy terminus, but it's all rolled up on itself with beautiful structure. That's really what we want to start talking about in this chapter. So let's bridge, though, from what we saw before, which was organic structures, amino acids and peptides. They had atoms and bonds, and all of a sudden we're looking at this mess. Well, let's back up and talk a little bit about the size. If we take 2, 3, 4, up to 10 amino acids and put them together, that's small enough for us to call that a peptide. A peptide is really the same thing as a protein in some ways, it's just a lot smaller. If we start getting up to more than 10 amino acids, we call that a polypeptide. And after we get to about 50 amino acids, we now call that a protein. And there is something that happens when you get up to about 50 amino acids, and that is the protein or peptide chain can now fold on itself and form a stable structure. Three-dimensional structure, that is. So that's some terminology that we used, and it also helps us to understand why we sometimes talk about peptides and proteins as if they're the same thing. There's really just a size difference. Now, in other classes, and in this class, and in reading papers and textbooks, we're going to sometimes use different terminology to talk about the size of amino acids. It's easy enough to say that a protein has a certain number of amino acids like we just did for GFP, but we often want to refer to the molecular weight. And there's an easy general average conversion. The typical amino acid has a molecular weight of 110 Daltons, and that simply means 1 Dalton is the mass of one hydrogen atom, and carbon has 12 Daltons in its molecular weight. So this is an average, though. Glycine would be a lot smaller and tryptophan would be a lot bigger. But it's useful for us to convert between number of amino acids and total molecular weight. For instance, we could say that if you have a protein with 238 amino acids, if we multiply that by 110 Daltons per amino acid, then we have a decent approximation of the overall number of Daltons in this protein. It turns out it's 26,180 Daltons. So that's gigantic. I mean, that's quite a bit bigger than the molecules we're used to talking about. By the way, since we get big numbers, much bigger than 26,180, this is not a terribly big protein here, we're going to see unwieldy numbers. And what we sometimes do is simply refer to this as 26 kilodaltons for thousands of Daltons. Maybe we'd call it 26.2 kilodaltons to keep 3 sig figs there. But this kind of terminology, kilodaltons, is how proteins are typically referred to with regard to their size. And proteins can easily get 100 kilodaltons, 200 kilodaltons, 1,000 kilodaltons. I mean, they can be gigantic, maybe a couple thousand kilodaltons, some of the proteins in your body. That's thousands of amino acids strung together and folded up. So we'll do some homework on this just to make sure you're able to handle this skill of converting back and forth between number of amino acids and kilodaltons.